So we've done a transformation example with dilation. Now let's move on to reflections and see how they're actually reflected or how they're actually represented on pre-image equations. So in this example here, we have determined the image after reflecting the equation y is equal to x minus 2 squared in the y-axis. So we're not doing the y is equal to x squared in this case here. And the main reason for that is because if you take y is equal to x squared and you actually reflect it in the y-axis, there's actually no change to our final function. If you imagine y is equal to x squared, it looks something like this. And you can see that if we reflect it in the y-axis, so the image is that the mirror would be this axis here. If you reflect it, then it's actually going to be the same shape. And that means that when you do your equations, you're actually going to get y is equal to x squared as a result. And just the numbers will work out that way. So what I've done is I've added a bit of a translation here by doing x minus 2 squared just to move the turning point and move the equation to the right so we can actually see how translation is actually reflected, or how a reflection is represented on our equation. So we're going to do exactly the same process as the previous video where we talked about dilations, and that's we're going to get equations for x and y, and they're going to be in terms of x dash and y dash, and that's going to represent what transformations we have. And those transformations are given to us in the table which is given in the description of this video. So we'll start off with our first step, x and y. Now, when we have a reflection in the y-axis, we can imagine that a point here, so for example, we have a point here which is 1, 1. If we reflect it to the other side or reflect it in the y-axis, then the x value becomes negative. So this will go to that point there, and the x value becomes -1, but the y value remains the same. And that's because the y-axis is the mirror, so when we reflect it from one side to the other, the x value is the one that changes. So in this case, what's going to happen is that x becomes -x dashed, and then y remains as y dashed. So these will be, actually I've got this the other way around, my bad. We should have equations for x dash and y dash. That's our first step. So x dash is equal to -x, so the transformed x value is equal to the negative of the original value, and then the y dash just remains the same. Y is unchanged. So then we do our next step, which is just rearrange for our traditional x and y. So we end up getting x is equal to -x dash, just multiplying both sides by -1, and then y remains as y dashed. And then what we can do is take these equations here and put it into our original pre-image. So what I'm going to say is that y is equal to x minus 2 squared. Therefore, y dashed is equal to -x dashed minus 2 all squared. So now we just have to do some algebraic manipulation. This looks kind of messy here. What we can actually do, you might have seen this before if you've worked with quadratic equations with these unique ones here. You can actually take out negative out of the bracket. So what that's going to look like is something like this. And we're just going to do it step by step just to make sure that everyone is on the same page. So what I've done is I've kept everything inside of the squared, which makes sense. But then what I've done is taken the negative out of there, but I still want the full thing squared. So I just have to make sure that I do double brackets here. Don't do this. This is not right. So -x dash plus 2 squared, because then the squared only applies to the bracket, but doesn't apply to the negative, which we still want to square. Sweet. Now, if we have negative something squared, that's the same as not having the negative in the first place, because if we had this bracket, or let's say we had just some sort of negative a times -a, that becomes positive a squared. It's the same as if we had positive a times positive a, that becomes positive a squared. So what we can actually do here is just get rid of the negative, and it's the same thing. So what I'm going to do is just say y dashed is equal to x dash plus 2 all squared. Hopefully that makes sense. We're just squaring an expression that's negative. It ends up just being the positive squared of that original expression. So therefore, the image equation is y is equal to x plus 2 squared. So the only thing that actually happened in this case was we changed our equation from x minus 2 squared to x plus 2 squared. And you might be thinking, how does that actually work? And what happened to the negative x? Where did that go? So in this example, because we have a quadratic equation, the negative you saw got squared out and became positive again. And that's because the shape of our quadratic equation actually doesn't change. When we reflect our quadratic equation in the x-axis, in the y-axis, sorry, what happens is that the shape doesn't change, but if we have a translation, then it just moves the equation across. So I might just check how much space I have on the recording. Okay, I got plenty of space on the right here. So let's just do a bit of a graph and see what's actually happening, because it's going to be really good to understand graphically what's happening, and then we'll see how the equations actually kind of correspond. to our transformed version of it. So our original function was x minus 2 squared. This is pretty much in turning point form, where you have a turning point at positive 2, 0, because you have the x translation, but then you don't have the y translation. So that's going to look something like this. So this was the pre-image. And this would be at 2, 0. Now, when we reflect it in the y-axis is our mirror, so therefore this equation is reflected to the other side. So we know it's going to look something like this. If we just base it off the mirror, it's going to look something like that. And this is going to be at negative 2, 0. So you can see the actual shape stays the same because quadratics are kind of multi-branch. So you have to the left of the turning point to the right of the turning point. And because it's a symmetrical shape, when you reflect the overall shape, the shape doesn't change. What's happening in this case is just it's moving across essentially. So you can see that the transformed version just has a turning point at negative 2, 0. And that's just because the turning point reflected from 2, 0 to negative 2, 0. But the overall shape stays the same. This doesn't usually happen when you do transformations with functions. Most of the time, you get a completely different shape. So I'll give you just a quick graphical example. Let's say if we had y is equal to the square root of x, you should know it looks something like that. If you reflected this in the y-axis, what happens is that you get a completely different shape. It's not like this where it's symmetrical. You just get that same branch that was there and you reflect it to the other side. And the equation doesn't cancel out a negative. You just end up getting y is equal to the negative square root of x. So you have a negative value inside of the function. That's how my teacher always used to describe it. When you change the x value is inside of the function. So therefore you have a negative inside the function that represents a negative or a reflection in the y-axis. It's not like this where you keep the same shape. It's a different shape. Or it's the same shape, but it's just reflected. In this case, you keep both sides or both branches because you have symmetricality. Now, in the table, it talks about a shortcut where you can do y is equal to f of negative x. F of negative x. Now, what you're essentially doing is just taking the x value and you make it negative. Now, this is actually the reason why if you have y is equal to x squared and you do f of negative x, it doesn't actually make a difference. So if we do y is equal to negative x squared, so we're just replacing x with negative x for our basic parabola, it becomes x squared again because you're taking something negative and you're squaring it. And this is pretty much an even function, right? You take negative x or you replace x with negative x inside of our function and it doesn't make a difference to your actual equation. So this shows that we're symmetrical about the y-axis. But in most cases, whenever you apply a reflection in the y-axis, you just have negative inside of your function. So for example, I had that square root function before. So if I do y is equal to f of negative x, what you get is y is equal to the negative square root of x. And that's, you can't simplify that any further. You have to keep it as negative x, but what you're essentially doing is just taking your equation and you're reflecting it to the other side of the y-axis.